You will recall that in a previous lesson, we said that the potential energy between two atoms that are bonded would typically look like this if you plot it versus distance. Okay, so your x-axis here is distance between the two atoms. Y-axis is potential energy. So, what does bond breaking involve? Bond breaking involves separation of the atoms. So that's increasing distance. So that's bond breaking. Okay, so you'll notice then that bond breaking involves an increase in potential energy. So your potential energy increases as the atoms move away from each other, and it decreases as atoms move towards each other. So potential energy decreases during bond formation. Now, like we said, if we change potential energy, that involves a corresponding change in kinetic energy. That's just the opposite. Okay, so what would happen if a reaction just involves bond breaking? Then that just increases potential energy, right? So that means a decrease in in kinetic energy of the atoms. That means the products are colder, right? Product temperature would be lower if there wasn't any flow of energy between system and surroundings. But basically what it means is it has to, if you're interested in the situation where you end up with products at the same temperature as the original reactants, then heat has to flow into your reaction mixture to restore the temperature. Okay, so we say then that bond breaking is endothermic. So we can expect this reaction, if it only involves bond breaking, then this reaction has to be endothermic. Similarly, you can make the argument that if the reaction involves only bond formation, then that reaction is going to be an exothermic reaction. In general, reactions, of course, involve bond breaking and bond formation. So it depends on how much energy is needed to break the bond and how much energy is released to form the bond to determine overall whether the reaction is going to be endothermic and or exothermic. So let's take a look at this question here. Classify the following as endothermic or exothermic, and what would be the algebraic sign of delta H in this case? So let's see. CH4 gives you carbon plus 4H. Okay, so you have CH4 molecules, methane molecules separating into just atomic carbon and atomic hydrogen. So the only thing happening here is bond breaking. Okay, bond breaking only. So you say this is endothermic. And if you have an endothermic reaction, heat has to go into your reaction mixture to bring the temperature back up. So your delta H reaction is going to be a positive number. Okay? Let's look at the second process here. You have two iodine atoms giving you I2 gas, a molecule. So the only thing happening here is bond formation. And if you have bond formation, then delta H has to be negative. Okay, so if this is going to be an exothermic reaction. Okay, if you recall, potential energy function for two atoms approaching each other looks like this. This is versus potential energy versus distance. The only thing happening is bond formation. For them to get stuck at this distance right here, if they were separated to begin with, okay, so if they have this much energy to begin with, for them to get stuck, they have to lose that energy for them to get stuck down here in what we call the potential well. And so that energy has to go somewhere else. It goes to this, eventually it goes to the surroundings. You have an exothermic reaction. And then the third one over here, well, imagine that as going from, remember, 2I going to I2 gas. The second one right here is exothermic, right? Delta H for this is negative. Well, to go from gas to solid, That's also an exothermic process. That's deposition. Okay, so it's sort of like bond formation in a way, because if you're going from gaseous iodine molecules to solid, uh, you're moving those molecules closer together. So except that the delta H for not that is not quite as big as for the formation of a covalent bond. This is just deposition from a gas to a solid.